So today's speaker is Dr. Sushil Gorai. He's an assistant professor at IISER Kolkata. Professor Gorai received PhD from IIS Bangalore in 2010. His main area of research is several complex variables. He was an Inspire faculty fellow at ISI from 2012 to 2015. He has written very nice publications in a reputed journals such as Proceedings of American Mathematical Society, International Mathematics Research Notes, Journal of Mathematical Analysis and Applications, Journal of Geometrical Analysis, and recently Proceedings of Royal Society of Edinburgh and Manuscript Mathematica. With such a brief introduction, I request Dr. Sushil Gorai to start his lectures.
Thanks, Vasu. Thanks to the organizer for giving me the opportunity to speak here, and thanks Suman for sending me invitation long back. Actually, long before. Okay, so I'll start with complex integration, which actually most difficult as well as most boring topic of complex analysis. When actually one student learned, but now it's kind of repetition for a lot of people, so it would not be that much boring, and you'll perhaps appreciate that this is actually the fundamental or the heart of complex analysis. Without integration, you basically not much of complex analysis can be done. All right, so let me share my screen. Can you view my screen? Yeah, is it visible?
Yes, yes.
Yes, sir. Yes, sir.
Okay. All right, so yes, I'm using my iPad for this one. So this is actually a little bit of new method sometimes.
Yes. It is clearly visible and
Yeah. In Google Meet, you can't see probably if I share just my iPad screen without anything. But here I'm using my MacBook as well as iPad. All right, so yeah, as I said, the development of this complex integration, or a little bit, one or two lecture, you'll find a little bit technical, but it lies in the heart of complex analysis. So I'll ask you a simple question. Suppose you have a sequence of functions in real line, which are actually expressible in power series. And if you know that it converges uniformly, let's say on every closed interval, can you show that the limit function will also have a power series just in real analysis? So this is actually a little bit of difficult problem. So the question is the following. If here what I would say, so suppose Fn is a sequence of continuous functions and Fn converges to F uniformly, then we know that F is continuous, right? Now suppose Fn sequence of continuous function on some domain. Let's say on if you like, open a closed interval. Now consider a sequence of smooth function, differentiable function. So maybe C infinity functions on, let's say, on AB. So which means it's infinity in a neighborhood of AB. And Fn converges to F uniformly. So what do you think? F is infinity? What do you think? Yeah?
Yes, sir.
Who said? Can you tell me your name?
The Manushree.
Okay. So yeah, this is actually not true. You know Westeros approximation theorem, right? Right. Everybody knows Westeros. I assume everybody knows Westeros approximation theorem, which says polynomials are dense in all continuous functions, right? In the uniform topology. So polynomials are C infinity. So hence a limit you get any continuous function. So this is not true. Now you say you look at Fn sequence of convergent power series. In the variable Ax. So convergent, which is convergent uniformly. Well, convergent on is good enough on AB. And Fn converges to F uniformly on AB. Does this imply F is also a convergent power series? Yeah, what do you think? It would be? Well, here I should mention a little bit. Instead of AB, you look at convergent on compacts on closed interval in, let's say, I would call it minus A to A, some number A positive, and uniformly convergent on, that is fine. Sorry, convergent on minus A to A and uniformly on compacts in the sense now compacts can be incorporated in closed intervals on closed intervals in minus A to A. Right? So the question is whether we will have also convergent power series. Right? So we'll see the answer to this question later. I mean, in the last portion of my talk, or maybe in the next, whoever gives you. All right. So, but it's not automatic here. Well, here you need to go to integration somehow. I'll connect it there, connect this one later. So maybe it's rather connected to the following. So Fn sequence of holomorphic function, which is analytic function, same as this, on, let's say, unit disk, and Fn converges to F uniformly on compacts of unit D. Does this implies F is holomorphic in D, on D? All right. So, so what we need is to prove this kind of statement is complex integration. So, and complex integration doesn't come from sky. It's basically coming from real Rayman integration only. Okay, so before going further, let me talk about a little bit about Rayman integration, very little. So here what we take is generally we take a function AB from closed interval AB to R, closed and bounded interval. And of course, we can do this functions to be a general discontinuous functions, but generally we'll, for this time, when defining complex integration, we will always assume continuity of F. So we just assume here F to be continuous. And then you looking at upper sum and lower sum, so you do this upper sum and lower sum, corresponding to a partition and corresponding to a partition, and then upper integral and lower integral right? So do you remember what is upper sum and lower sum is corresponding to a partition? So let's take partition A, B, x1, call this x0 as A, x2, and so on, and this xn equal to B.
So
Yeah.
maximum value on AX1 multiplied by the length, and similarly
Yeah.
each interval. So that's upper sum, and similarly minimum value multiplied by the length is lower sum.
And then you take summation, right?
Yes.
Yeah, you take summation. So here, the upper sum is summation over J corresponding to this partition. You have capital Mj, which is supremum of Fj, F on xj minus 1 to xj, and this xj minus 1. And similarly, lower sum would be summation over J, small mj. Similarly, small mj will be infimum xj minus 1. All right. And then you take, so what do you take the upper sum? Infimum, right? And you take supremum of the lower sums, overall partition, right? So upper integral will be infimum over all infimum of upper sum. So over all partition, and lower integral will be again supremum of lower sums over all partitions. All right. So, and then integrable. Sorry. F is integrable or Riemann integrable if upper integral f t dt, let's say a to b upper is a to b f t dt lower, and this actually one would define integration a to b f t dt, right? We'll use this. We'll use this one, this Riemann integral of the function f to define our complex integration. All right, so for complex integration to start with, so we'll start with complex integration. So here you have to look at complex valued function first. So to begin with, you start with a function from a closed interval AB to C instead of R. So here we get the change, right? And you define similar way integration f t dt, integration AB. So f is continuous, and now since it is complex valued, so ft will be ut plus ivt, right? So the integration will be defined as integration a to b ut dt plus I integration a to b vt dt. All right. So do you have any problem in defining integration ft dt in this way? Any question here?
Sir,
Yes.
so in case of complex integration, is it not possible to define integration over non-continuous functions?
Well, yeah, you can define, right? See, here we are using this Riemann integration. So this one, this is nothing but Riemann integral.
Yes, that's fine. So we do not need it to be continuous in the
Right, Riemann integral, and here this is also Riemann integral. So you don't need continuity at this point. Defining function or defining integral in this way. So, and function, look at here, our function is defined on an interval. So from interval to define integration, you don't need continuity of the function. What you need, this real imaginary part should be Riemann integrable. All right. So maybe let me put it that as a note. So call this one. So note to define
Sir,
integral.
hello.
Yes.
Sir, can we define integration of space filling curves? Because if we don't assume continuity, it can be a space filling curve. No, sir?
We have not gone to the curve.
We cannot
right?
take.
Did we define integration over curve? No, we just look at here. Our function is
Yes, sir.
nothing but our function is from AB, right?
Yes, sir.
We
Sir,
are
but
not-
there are space filling curves, sir. So because AB can map to whole space,
I
that time
mean,
we cannot take one variable, no, sir. If we drop continuity, then can we do that, sir?
no, the space filling curve is continuous also. So that doesn't actually see here when U and V are you using separate thing, right? U and V, and you know
Yes.
U and V, if it is continuous or if it is Riemann integrable, this makes sense. So hence this makes sense.
Yes.
So there is no problem here. So whatever image would be.
Sir, in the definition, can we draw continuity? Instead of that, we just assume that function u and v are Riemann integrable.
Well, yeah, that's possible here. But for the purpose later on, we'll need continuity. But for this definition, for a function in an interval, note you cannot define holomorphicity here. You are looking at an interval. So here you can define integration in this way.
No, I'm just saying that can we drop continuity, that it is written that function is continuous function. Can we drop that continuity part?
Yeah, here if u and v are Riemann integrable, then you can define.
Yes.
Then this makes sense, hence you can define. So there is no problem here. So to define integration, as in here we are not doing any functions on complex domain in complex plane. We are working on an interval in real line, but complex valued function. In this case, in this definition. So to define integration, as you know on, we do not require continuity of f. We just need that the real and the imaginary part.
Dr. Sushil, your screen is not visible.
Oh, it's still not visible? Okay. Just
Writing screen is not visible.
is it visible now?
Yeah, now it is visible. Thank you.
Okay. So this is important. So I can't see you who's speaking. Okay, I was trying that. Okay, so real and imaginary parts are Riemann integrable. All right. So two most important. One most important theorem in integration is the fundamental theorem of calculus, right? So fundamental theorem of calculus will play a big role here also. So the fundamental theorem of calculus. So this will play a big role here also. So let me write it in as we had studied in real variable. So let f from AB, an interval in real line, to R be continuous. Define capital Fx to be integration a to x ft dt. So this would, you will see, keep on coming again and again, this type of integral. Then f, capital F, actually, capital F is differentiable and f prime x is equal to small fx. So this is, maybe I should write it down there. F prime x is fx for all x in AB. All right. So this you know, right? Yeah. If you forgot the proof, you just go back and after going back, you just try to remember. This is a very important theorem, so better know this perfectly. So second one, the same. This is also called fundamental theorem of calculus. Let h be a function from AB to R be differentiable such that h prime such that small h is capital H prime. Small h is just continuous. Is continuous. Okay. So small h function, which is equal to capital H prime, is continuous function. Then integration a to b ht dt is hb minus ha. This we actually do from schools onward. Try to find capital H so that we can do the integration. All right. So now these two are very important things. So an exercise here. Prove the formulate and prove, maybe formulate and prove the fundamental theorem of calculus and for functions f from AB to C, right? So what I want is the following. Instead of R here, you change it to C, and your integration is defined this way. And now you prove this fundamental theorem of calculus. Okay, the statement would be as same as it. So, of course, the one part of the exercise is to formulate. So, how do you formulate a theorem? You just prove it first. Prove something first. So here, as you do here, if f is from AB to C, then what happens? You do for real and imaginary part correspondingly and see what comes, and then you formulate. All right. So here also you take h to be functions from AB to C and differentiable function, and h, small h is capital H prime, and then this one. All right. So this is an exercise. Now let's go to the curves. So now curves, arcs, paths. So you have seen several these things, right? Curves, arcs, path. So first thing is that we'll make this assumption: we will not distinguish between curves and arcs. So curves and arcs will mean the same thing, but path will actually path, to say something is a path, you need to give the initial and terminal points. So path will have initial and a terminal point. Maybe that's not it. All right. So you might have seen several books where curves will be defined as kind of some equivalence class and all those stuff. So we'll not consider anything, any equivalence class or anything. We'll not distinguish. So let me define first what we want to mean by a curve or arcs, whatever. A curve is a continuous map gamma from, so a curve gamma is a continuous map from some interval AB to C. Okay, so this will also be called as arc if one likes. So this will also be called an arc or a path from gamma A to gamma B. All right, will not distinguish as such. So it's better to keep the same. If there comes any problem, then we'll tackle that. All right. So any question here? Okay, so what will work mostly with smooth and piecewise smooth curves. So let us see what, let us first we define what does, or let us try to understand what this means, right? So definition, we say a curve or arc or an arc is smooth if so a arc gamma from AB to C is smooth if gamma prime T exists for all T in AB. So at the end point, we'll take one side limit. All right. And gamma prime is continuous. So we'll just look at continuously differentiable maps from an interval to C as smooth curve. All right. and piecewise smooth. So a curve is, let's say gamma, again, from AB to C is said to be piecewise smooth if it is smooth except finitely many points. Which means that is there exist points T1 less than T2 and so on less than equal to Tk. It can be A as well as B, such that gamma is differentiable gamma is smooth except T1, T2, Tk. All right, but here gamma remains continuous at all points. Okay, so we are not removing continuity. So when there is a curve here written, which means gamma is continuous, so continuity remains, but differentiability may be lost at few points. Well, let's look at examples. I have not given example till now. So look at a circle, right? Okay, we'll start point for like here. So maybe this is the point 1 and this is 0, center at this one, and it goes like this. So gamma t is e to the power it on 0 to 2 pi. Smooth curve is a smooth curve, right? And next we look at rectangle. Right, so gamma is so I'm just giving you what is this. So this here is piecewise smooth. So the two most important curves will be the following. So two most important curves. So one is circle, as I said, gamma t is a plus e to the power it, t belongs to 0 to 2 pi. This is a circular arc. And second one, so gamma t is say z0 plus well, I should rather write the following: t z0 plus 1 minus t z1. So can you tell me what is this? So t belongs to closed interval 0, 1. Can you tell me what is this curve?
Straight line.
Right, right. So straight line. So yeah, so this is, if it is Z0 and it is somewhere Z1, and the line segment joining Z0 to Z1 will be this one. So here now you know, once you have these 4 points, you can get the rectangle by using this curve, right?
Sir, it's a line segment joining Z1 to Z0, I think.
T equal to 0. Yes, you are right. So maybe I'll that is correct. Thanks. So maybe I put here Z1 and here I put Z0. So T equal gamma 0 is Z0 and gamma 1 is Z1. So it goes this way.
Sir, what will be the radius and center in first case, circular arc?
Oh, here in this, right. So here, yeah, thanks for this telling me this one. So I should write here an R e to the power it. So here circular arc with center A and radius R, right? So this two will be very important. So in almost all the theorems, you will see this either appearing this arc or this rectangle or triangle. To get rectangle, triangle, you need 2, and for circular region, you will need this arc or this curve, gamma t a plus r to the power it. All right. So these two are kind of most important. Okay. So now a note. So if you so what I want to see is change of parameter. So you see here the t is the parameter, right? T is the parameter. So if we change the parameter, then what happens? Right? So first define what is the change of parameter. So a change of parameter is a non-decreasing map phi of, let's say, a prime b prime to onto map AB, and there this parameter t will be represented by phi of tau. So exercise, smoothness slash piecewise smoothness remains invariant under the change of parameter, provided the change of parameter phi is smooth. a smooth imply is continuously differentiable. So is continuously differentiable. Okay. So we'll not spend much time on this. It is an exercise, and we'll come back with again change of parameter when we when we define the integration. Any question till now? Couple of more definition. A simple. So this is also definition. A simple so gamma from A to B to C. So a curve is called simple if gamma T1 equal to gamma T2 for A less than T1 less than equal to T2 less than B implies T1 equal to T2. So what it means? It means you can start from somewhere and go somewhere. This is simple. You start here, and this is gamma A and this is gamma B. So here it's gamma A and it's gamma B. This is not simple, because this actually you have 2 points, while let's say going from this side and coming from this side, there are 2 points which intersects here. So this doesn't hold. So here I deliberately put a condition A is strictly less than T1 and T2 strictly less than B, which means it can intersect at the end point, which means it can be closed. So if this is gamma A and this is gamma B, so this is simple. All right. Well, here from the picture, it is not at all clear. It is just to understand this one. So you need to look at the parameter, how the parameterization looks. Then you can realize then that whether it is simple or not. Okay, I'll come to that example. So maybe next definition. So curve gamma from AB to C is said to be closed if gamma A equal to gamma B. So therefore, a curve. So this is closed. So this is closed as well. So curve gamma gamma from A to B, AB to C is called a simple closed curve if it is closed and simple. So this is obvious. All right, so here is note of caution. So one should not be confused about the trace of a curve gamma, which may be denoted by, let's say, box gamma, something like that, and the curve itself. Right. So the point is, you should not confused with the picture to the curve. Generally, we consider the simple closed curve most of the time in the proof. So you should not be worried. And clearly, whatever geometry you are seeing in the picture, the same get translated there. All right. So here, let's say this is A and center, and this is radius R.
Sir, what is trace of a curve, sir? What is trace of a curve?
Trace of a curve is the image of a curve. So this is the image of gamma in C. Okay. So for example, this one. Look at this example. Gamma 1t is A plus R e power it. Right? 0 to 2 pi. Let's say gamma 2 t is A plus R e power 2 it on 0 to 2 pi. So this one I previously told you it's gamma 1, right? So what is gamma 2?
Same circle repeated twice.
See? So trace of the curve in this case, trace of gamma 1 is actually trace of gamma 2, but gamma 1 is not equal to gamma 2. Two curves are not same. Okay. So you should not be confused between the trace of the curve and the curve itself. So curve can be generally parameterized differently. It may pass twice or thrice, whatever. But most of the time, when we apply somewhere, one generally takes the most simple one, this one. So when it's applied to some other places, you should not be worried if one is saying that we are integrating on the circle. So we are integrating on the circle, it will mean that we are integrating on this curve gamma. Okay. With the parameterization of this one, on the interval 0 to 2 pi, this one. All right. So this will come next. So few more, let's go back to the integration. So few more, let me put few exercises for the tutorial. So that integration A to B ft dt conjugate is integration A to B ft bar dt. Like f is from as before, AB to C, continuous. Second thing is integration A to B C times ft dt is C times A to B ft dt. Right? This is obvious. Just go with the definition, nothing else. Unfolding definition, it would work. Third one, integration A to B ft dt less or equal to integration a to b mod ft dt. Okay, so this one you need to do some work here, but I think it is easy. So maybe it should be done in the tutorial. All right. So with this, so let us define integration on a smooth arc or curve, right? So as we considered gamma AB to C, smooth arc, smooth curve, so you see gamma can be written as gamma 1t plus I gamma 2t, right? And f is a continuous function on gamma. Here you see, here we are deliberately considering here the trace of gamma. You should not be confused about that. When you say f is continuous on gamma, you are always meaning the trace of gamma here. Okay, trace. So in the books, you will find this, the continuous function on gamma. So here we mean f is continuous on the trace of gamma. Okay. Right. Otherwise, gamma is a function, right? Then continuous on a function. What does it mean? Right. There are two things. So one is one should not be confused when one is talking about a curve or a trace of curve. But here precisely, it's basically it's a traditional that one says that f is continuous on gamma, which means f is continuous on the trace of gamma. Then we define integration over gamma fz dz as integration over ab f of gamma t gamma prime t dt, right? So this is the definition of integration on a curve. Is this clear? The right hand side makes perfect sense, right? As we did here. Here, as we did here, right? So since this makes sense, so right hand side makes perfect sense. Yeah, any question?
Any geometric meaning of that?
Can you be a little louder?
The geometric meaning of defining like this. The geometric idea.
Geometric meaning. Yeah, I'm coming to that. So you can say it in a different way also. So let me go into this one. Geometric, when you want to geometric meaning, well, here it's nothing but area of this, right? Area under curve, under this. It's integration on EB, right? And this is of course here it is U plus ID will be that form, and then real part and imaginary part will have different geometrical interpretation. But there are interpretation from the calculus point of view, which let us go into that. Okay. So in calculus, you have seen path integral, right? Have you seen path integral?
Yes, sir.
Okay. So let us interpret this one in terms of path integral in R2. Let us see how that can be how that can be done. But before going into that one, let me write one final thing. So this one I'll call 2. So here we define for smooth curve, but it's 2 makes perfect sense for piecewise smooth curves. All right. So instead of just smoothness, smooth curve, one can do piecewise smooth. One can work with piecewise smooth curve. So suppose gamma from AB to C is a piecewise smooth curve. Well, such that gamma is smooth except the points, let's say T1, T2, Tk. Inside, of course, this is inside A and this is inside B. So then integration over gamma. So let me draw the picture. So that would be good here. So this is gamma A, gamma B, let's say. This is gamma T1, gamma T2, gamma T2, gamma T3, and so on, gamma T4. So then integration over gamma FT, FZ dz or FDZ, both the same. This should be defined as, now you see gamma prime T1, gamma prime T2, and so on are not defined. So this should be summation over j equal to 1 to k, integration over a to, well, a can be seen as T0 or maybe Tj, that is fine. No, this is fine. We will start from which is, let's say, gamma T0, and here this will call gamma of T k plus 1. So we start with, or maybe call Tk. So start with 0 to k, T0 or Tj to Tj plus 1 f of gamma t, gamma prime t, or gamma prime t, which is t dt. If you want to write this one as part, this is gamma 1, this is gamma 2, this is gamma 3, and this is gamma 4, and so on. If we represent this one as this is gamma 1 and this is gamma 2, this part is gamma 3, this part is gamma 4, and so on, then it will also be similar to same as j equal to 0 to k integration over gamma j fz dz. All right.
Then the summation will be from 0 to k minus 1 or k?
Yeah. So you are right. Yeah. So maybe it's better to write this one as k plus 1, right? I want to put it in 0 to k. So yeah, thanks. 0 to this, so this one k plus 1. So 0 to k makes sense, right? Now? Yeah. So this one I consider as T0, and this is Tk plus 1.
Sir?
Yes?
Can you use the concept of partition and upper sum, lower sum to define the complex integration?
Well, this will be then the repetition of, again, what Rayman integration you did in R, right? So you need to look at real part and imaginary part and so on. Go on doing this one.
No, for function from curve to C, from a gamma to C. For a function from curve to C.
Well, then you need to look at this modulus and stuff. So you can see Conway's book, which Conway shows it in terms of more general curves, which is rectifiable curves. So curves are with bounded variation. So there you will see that he looks at some partitions and he develops that one. So lower sum, upper sum might not be available now because you will not have this less than and greater than inequality. So when you look at complex value, so that ordering is gone. So lower sum, upper sum you cannot do, but Riemann sum part will make sense. So that part you can go through that way. So does that answer your question?
Yes, sir.
Okay. All right. So this is all about this piecewise smooth curves. So let us look at the calculus point of view. So from calculus in R2. Calculus. Okay. So here, so f was a function from, well, continuous on gamma, right? So f will be u plus iv, right? And gamma was gamma 1 plus I gamma 2, right? So these things, this you can actually write in the following way. So what is z? Z is x plus iy, right? So you must have seen Cauchy-Riemann equation in the form of del by del z bar of f equal to 0. Have you seen it?
Yes, sir.
Okay, so you know what is del by del z bar. So similarly, one can actually look at dz. as dx plus I dy. Okay. There are geometrical interpretation of this one from complex geometric point of view, which is out of scope of this course. But yeah, we'll not go into that one. But here, algebraically, this makes perfect sense. And this is kind of dz is dual of, lies in the dual of del by del z. All right. So similarly, if you write d of z bar, which is actually dz bar, which is dx minus I dy. All right, these two notation will use. Okay. So now next you write in terms of f integration over gamma f dz. So we view gamma as AB to R2 smooth or piecewise smooth. So gamma t will be gamma 1t, comma gamma 2t. All right. So now this one integration. So this is a path now, right? On R2. Now this one will be nothing but u plus iv and dx plus I dy. So this one, if you multiply u dx minus v dy plus I times integration over gamma v dx minus u plus u dy. So gamma is now a curve in R2. So we look at the real and imaginary part as path integral in R2, right? So you know integration. So we know this from, we know integration over gamma p dx plus q dy, right? This is a path integral. So both the integral of 3 is or are of the form four, right? So does it make sense to define f dz in this form, two path integrals? Yeah.
Yes, sir.
Okay, so it does make sense, and we'll show in a moment that these two are same. The way we defined earlier will be the same as this. So recall. So comparison between two viewpoints. So recall integration over gamma p dx plus q dy is defined as integration to a to b. So gamma is ab to R2, right? And gamma is equal to gamma 1 comma gamma 2. In C, it was gamma 1 plus I gamma 2. So this is defined as P of gamma t, gamma 1 prime t dt plus Q of gamma t, gamma 2 prime t dt. See, we did not do different things. We just actually did whatever is done for path integral. Now you write this one. So now with this definition, you look at, so with this definition, we look at the real and imaginary parts of this one, so the real part and imaginary part of 3. So then, so what we get is real part what was it? It was gamma u dx minus v dy. So this one, integration a to b u of gamma t, gamma 1 prime t dt. Well, dt we can take common, so we can take out. And similarly, v of gamma t, gamma 2 prime t dt, right? And the imaginary part, so what was it? It was v dx plus u dy. Integration v dx plus u dy over gamma. This is integration a to b. By the definition here, like this, with this definition, v of gamma t, gamma 1 prime t minus plus u of gamma t, gamma 2 prime t dt. All right. Now look at the integration f dz or fz dz over gamma. These two will mean the same thing. This is nothing but this real part plus imaginary part, which is here. This one, maybe can I do it? Can I just copy and paste? Right? So this one. Then you look at, do a little bit of computation, and you see this is, do this computation a little bit. So what you see is a to b u of gamma t plus I v of gamma t, since I have done it already, so you can do it. And this is gamma 1 prime t plus I gamma 2 prime t dt. And this is nothing but integration a to b f of gamma t gamma prime t dt, which is, so this was our earlier definition, right? So we did not do anything new. What we did is the analogous to the real variable we did as in complex variable also, but this matches with the path integral in R2, which comes from calculus. So this is nothing different from calculus. All right. Yeah, so maybe a few exercises. So more exercise. So that integration gamma f dz remains invariant under the change of parameter of the curve gamma. So this can be done very easily using just the definition, unfolding the definition. There is nothing new here. All right, I have 7 minutes. So maybe
Sir, give some example, sir. Example.
That I'm thinking, yes. That I'm thinking. Yeah, so maybe I'll just give you a few examples. So for example, consider fz to be 1 over z, right? And gamma is gamma t equal to, gamma is a circle, or maybe gamma t equal to e to the power it, t belongs to 0 to 2 pi. So instead of one would write just gamma is equal to mod z equal to 1. One would write like this. So this is the standard parameterization for this, for the circle, right? As I mentioned, I repeat here. So here, so this is 0. This is just 1. So you see here, integration, by definition, it will be 0 to 2 pi f of gamma t, gamma prime t dt. So this one, 0 to 2 pi, gamma t is e to the power it, so 1 over e to the power it, gamma prime t, which is I e to the power it dt. So here this goes away, this goes away, so this is just 2 pi I. Well, what happens if you look at a circle inside, right? So this was gamma, let's say this is gamma 1. So if you integrate on gamma 1 f dz, same f, which is nothing but 0 to 2 pi. Now gamma 1 t is r e power I t, t in 0 to 2 pi, same. So f of gamma t, gamma prime t dt, right? So integration 0 to 2 pi, 1 over r e power I t, and gamma prime t is again r I e to the power I t dt. So now this goes away, this r also goes away. So the integration remains same, 2 pi I, for the small as well as the big circle. All right, now you look at another circle.
So does it any relation with area or something like in integration in R? What is the meaning of that 2 pi I? What 2 pi I will give? Geometrical significance, sir?
Geometrical significance will, in this case, so it depends on the particular function, right? In this case, geometrical significance will come later. So in this case, the geometrical significance will be how many times gamma moves around the point 0 times 2 pi.
Winding number.
That is the winding number, right? So the interpretation, you cannot interpret like area of something, and this one, complex integration will have different interpretation in different context. So in this context, these things will give you the winding number of the curve around 0. So you see here, and that is the reason gamma 1 and gamma 2, and take any circle around 0, smaller or bigger, will have the same integral. Right? Now if you look at the same example, and now curve is different. Suppose gamma t, so gamma 2t is, let's say it's a circle centered at 3 by 2 and radius half. So here if we draw, it would be something like this, something like this. So if this is gamma 2, then what happens? So gamma 2 will be of this form, 3 by 2 plus half e to the power I t, t is in 0 to 2 pi. So here you integrate again, integration gamma to f dz, which is nothing but integration 0 to 2 pi. Well, before going into 0 to 2 pi, this is fine, 0 to 2 pi. 0 to 2 pi, f of gamma t, gamma prime t dt, which is gamma 2 here. So this is nothing but 0 to 2 pi, 1 over 3 by 2 plus half e to the power I t, and then gamma 2 prime t, which will be half, and then I e to the power I t dt, right? So now this is little bit complicated, right? So 0 to 2 pi, your half would go away. So I will remain, and then you have e to the power it, and below let me take 3 common, which is 1 plus e to the power it by 3 dt, right? So now what you need to do is you expand this into, so I by 3, 0 to 2 pi, and you expand this as a power series, right? Summation k from 0 to infinity e to the power it by 3 whole to the power k dt, right? This converges uniformly, right? This makes sense. This will be less than 1, so it makes sense, right? Now you can interchange the summation and interchange the summation and the integration. So this will be, this you can do because the uniform convergence of this power series I by 3, and here summation k from 0 to infinity e to the power ik plus 1 t.
So I think the series is
minus should be there, right, sir?
alternating series.
Minus should be there, sir. Minus sign. Alternating series you will get.
Oh yeah. Minus 1 to the power k, right? Something like that. Yeah, that is fine. Minus 1 to the power k. Actually, it doesn't bother here. T by 3 to the power k dt. So what you have is this integration will be 0. All the integrations will be 0 because this k is not minus 1, right? So here what we are using is integration e to the power it ikt 0 to 2 pi is what? Dt 2 pi when k is 0 and 0 and k not equal to 0. All right, is this fine? Yeah, you check this. So this integration will be 0. So the winding number 0 doesn't lie inside that curve. So that makes perfect sense. Yeah, so any question? I'll stop here for today and we'll look, I'll continue tomorrow. Yeah, any question?
Sir, curve must be a smooth curve in the integration of the contour.
No,
Is it necessary?
No, piecewise smooth is good enough. So piecewise smooth, for example, you can do with rectangles. Instead of circles, you can do with rectangles also. So I'll send an exercise tonight, maybe tomorrow in the tutorial, or tomorrow I'll give an example with rectangle. Piecewise smooth good enough. You can actually work with more general curve, but that makes your life complicated. So piecewise smooth is good enough for whole theory to work.
Sir, here winding number is 0 like that, sir. So what is that meaning, sir?
It's a winding number roughly means the curve, how many times the curve moves around that point.
Okay, sorry. Okay, sir.
Yeah, this can be, this is very topological, but this can be written as an integral. So in this series of lectures, I have that topic. So I'll give few times on winding number also. Okay, so I started a little bit slower today with a lot more from Rayman Integration stuff. So tomorrow I'll be a little more faster if I have to complete whole thing. Yeah, any other question?
Yes, sir. Sir, is this integration path independent? For instance, if we had just 2
So
points
you
on,
mean, yeah, you mean whether the integral is dependent only on the endpoints, right?
yes, sir.
Yeah. So we'll give a necessary sufficient condition tomorrow. And my plan was to give it today itself, but you will see it is very clear. It is very interrelated with the calculus in R2, and in complex analysis, automatically Cauchy-Riemann will come in the path independence theorem. So when the path integral dependent only on the endpoints. Just in this question, you have if and only if condition even in R2. Now, if you look at that condition for a complex valued function on a domain, you will automatically get a certain Cauchy-Riemann equation. Okay.
Okay, sir.
Yeah. Any other question?
So if there are no questions, let us thank Professor Sushil Gorai for a very interesting lecture and giving from the very basic, bringing from real analysis to complex analysis in integration. So Professor Sushil, can you just share your PDF file of this one?
Yeah. This one I'll just share.
Yeah.
So I'll send you an email, or
you can send it to Suman so that he will circulate to all the participants.
Okay. Yeah, sure. I'll send it to Suman right now itself.
Okay.
Okay.
So thank you, and let us have a break. After that, we will have a tutorial session.